Hello, hello. Chapter 8, Energy. We're in section 8.5, Kinetic Energy. And we're going to start off with a definition. Kinetic energy is defined as the energy of motion. That makes sense because the word kinetic comes to us from Greek, where I think it was kinesis, just meant movement, something in motion. If you want a different definition, you can say the energy due to the motion of the object, because the object that has kinetic energy has to be in motion. Just another way of saying it. There's two main categories of energy: kinetic energy, and we have a few examples there. A moving baseball can do work. You know, if you get hit by a baseball, it hurts, and it takes energy to hurt you. Falling anvil, a falling hammer can do work, especially when it hits the nail. Then there's potential energy. We talked a lot about gravitational potential energy yesterday. And there are other types of potential energy, like mechanical, because if you compress a spring, that's putting energy into the spring as you compress it. Now it has the potential to pop out. Chemical potential energy, like the energy in gasoline. Nuclear potential energy, the nuclear is stored in the nuclear bonds between protons and neutrons. And energy can be converted between types. The gas in your car has chemical potential energy, and when you put it in the car, it turns it into motion, kinetic energy, because the car goes moving down the street. We've talked about that before in this class, and you've talked about that a lot in chemistry class and other sciences. So I just wanted to throw that out there now. We're actually going to talk more about converting energies tomorrow. And how do we figure out how much kinetic energy something has? Well, we have an equation. Kinetic energy equals 1/2 the mass times the velocity squared. You should write that down in your notebook. Oh, wait, you don't need to write it in your notebook because I'm giving you the notes. So if you have that open, you'll see that in there. What's next? Okay, kinetic energy is proportional to the velocity squared. So that means you need to watch out for fast things. Here's an example. How much it hurts to be hit by a car depends on how much energy the car has. So, would you rather be hit by, okay, don't freak out on me, that picture in the bottom right is of a Hollywood stunt double. That's not just some poor guy getting hit on the city street. And you can tell because the cops and everybody in the background is looking at him. They're out of the camera shot. I forget what movie that's from. Something not too long ago. You can also tell because that car is not, well, several years old. Anyway, so this picture is of a Hollywood stunt double. It's not a real accident. Question number 1. Would you rather be hit by a car that is twice as heavy as the car in the picture? Or would you rather be hit by a car that is moving twice as fast as the car in the picture? And I can tell you this for sure. They're not the same. So, would you rather be hit by a car twice as heavy or a car twice as fast? Please give me an answer, A or B. What's your answer? Thank you. Now, let's see what the right answer is. A car that is twice as heavy as the car in the picture. So there's the equation up top. And if you double the mass, you can see then you're going to double the kinetic energy. And then B, if you double the speed, well, you square the speed. So if you double the speed, then you also double the 2 that you doubled. So the square of 2 is 4. So now if you double the speed, you've quadrupled the energy. Do you see? So, would you rather be hit by? The correct answer is A. You'd rather be hit by a car that's twice as heavy because then you get twice the kinetic energy. But if you double the speed, then you're going to be hit with 4 times the kinetic energy. And that is going to be twice as bad for you.